So, yeah, let me start maybe by introducing myself before I share the screen and go through the the details of the talk. So my name is Emre. I'm a professor at The Ohio State University. My areas include information theory, AI, machine learning, historically, the general area of data science, covering data security and data communication. But information theory is at the core of it. Before Ohio State, I was at MIT, doing my master's and PhD under the supervision of Bob Gallagher. He was great in information theory. So I am very new to the area of active inference. And in fact, I'm thankful to Maxwell for getting me into the area. I was presenting a problem on medical science, and he basically said, hey, all of this, you should look into active inference. And, it's a great mapping from what we have there to what you're trying to solve. And indeed it was. And this happened like roughly 6-7 weeks ago. So when I say I'm new to the area, I mean it. Okay, I really mean it. And, my advisor always said, like when you're starting working on an area, before you go ahead and read everything that's published and program your brain, what you should do is you should just give it a shot on your own. Try to solve some of the core problems. I mean, obviously, I'm not claiming that I'm solving core problems, but with that state of mind, when you start reading other people's work, it will be a very different perspective. So in fact, that's kind of Claude Shannon's perspective as well. And, I like doing that. And that's what I did. And in the last 6-7 weeks, I got myself accustomed to the way of thinking that I kind of envision these things should be thought about. Hopefully, I mean, it's going to be a different perspective for you guys. I'm hoping, okay, maybe many of the things that I'm saying will be repetition of things you already know or somebody else already solved. If that's the case, I apologize, but hopefully it's not going to be a waste of your time, okay? So if you have a question like, hey, haven't you read that paper? I probably haven't read that paper. So just warning upfront, So let me share my screen, and I'm going to tell you what I will be talking about very briefly. I feel like it's important, again, I'm coming from dynamical systems and information theory. I thought it was important to give my perspective, introduction to active inference, some of the very basics to set the stage. So I'm going to start with that, and a few interpretations pertaining to information geometry. And then from there, I'll basically present a very interesting, in my opinion, observation in dynamical systems. And lastly, I'm going to give an application, a solution of a problem in cancer treatments, which is motivated by, my solution is motivated by active inference ideas. It's going to be a little mathematical. I'll use a lot of notation. Hopefully, I'm going to be able to make things more intuitive. So if you get lost in notation, please don't worry. Please don't fall asleep. I'll try to talk a little into that and try to make things intuitive, okay? So a little to start, motivating a bit about my journey, slightly more about my journey. I have been, again, as I said, working on information theory. So let me tell you, in my opinion, how, active inference relates and bridges a gap between information theory and each one of these respective fields, like systems and control theory, machine learning and optimization at a high level. So all three of these are areas that I have in the past looked at, okay? So when you look at systems and control theory, information theory feeds that by adding constraints on transmission and information. For example, if you're controlling a plant, what if you have a constraint on the rate of communication between your controller and the plant? So those are type of the constraints that you can handle through information theory. But that's pretty much the level that, information theory directly, affects that field. On machine learning, information theory presents relevant metrics, and those metrics are naturally integrated into some of the problems, again, as constraints, and as you perhaps try to understand some of the basic limits. But historically, what I've been trying to do is add information theory to these fields in such a way that there's like a physical significance. There's like a functional significance of some of the concepts. For example, hey, we have a very well-established linear systems theory and input-output relationships using things like transfer functions, like historically and more modern tools. But we don't have the same need theory as it pertains to concepts such as entropy. What is input-output entropy, and as an example, right? And I was trying to work on that, and active inference was very refreshing because it is yet another perspective to achieve that bridge, right? Quantification of information through active inference. And as you're solving, for example, some sort of optimal control problem, active inference bridges things like, hey, what's the free energy associated with a physical significant meaning there? What is the entropy, and so on and so forth. And likewise, when you're working on machine learning and optimization, you can add physics-informed optimal control through concepts in active inference. So it was refreshing, and I have been thinking quite a bit about it in the last few weeks. And, again, as I said, I'm going to be sharing my insights. I know I was told that the Q&A session is at the end, but I'm happy to answer the questions rather than them accumulating on and on. Please stop me with any questions that you may have, if that's the format that you prefer, okay? So here I'd like to introduce a few notation, all right? So, I want you to remember some of these so that it will be hopefully helpful as we develop it. This is like a very classical single in, single output dynamical system. I represent the system state with X, okay, except like classical notation, all right? This is the system state. System is evolving, pertaining to, for example, neurobiology or neuroscience. Let's think of this as outside of, my direct agent, right? It's some system evolving. It may be within the agent itself, like for example, cancer tumor, but it's like this variable that's evolving, right? And then there's the sensory variable, which I use Y to denote. It's kind of the output of the system in classical dynamical system, but I view it as the sensory variable, right? So this is what's exposed to the agent, but the agent doesn't use the entire information included in this variable, the sensory variable Y. That's where the perception comes in. That's where, the limited information in my title also comes in. There's perception, which means take this Y and summarize it in some form, which is denoted by Zn, okay? So it's kind of the limited version of Yn. How can it be limited? Either sort of resolution, or perhaps in, for example, you may want to sample the output every once in a while if you have limited feedback budget. For example, if you're treating a patient, like a cancer patient, Xn denotes the tumor size, you don't have the ability to, or the budget to observe or give a CT scan to the patient every 2 hours, right? So it's in the sensory variable there, it's available at the output, but you only sample it once a week or once every other week or something like that, depending on your budget, okay? And then the controller depends on my perception variable, so only limited information is available to me to control the plant, and I take action accordingly. And one action is from the set of viable actions, which are going to be affecting Xn, as I'm going to be showing in a second. But one important thing here is that I added delay here, which is very typical 1 unit of delay, which means my action at time t affects the system state at t plus 1. So I prefer to put like that 1 unit of delay there. So just to summarize the variables that are involved, there are like 3 sets of variables as I devise the problem. They're external variables, which is your system state in this simple model. They're internal variables, which is, you know, your perception output, okay, the internal variable. And then there's the Markov blanket, which is simply, I mean, conditioned on these variables, y and a. The external and internal variables are statistically independent, okay? So as you can see, you know, my perception affects the action that I take as a function of the action that the perception that I have. And my action at time n alongside the state in the previous state, stage, affects the next state. And my control action also involves what to observe next. For example, I not only take an action to give chemo in the therapy example, but suppose I also make the action or choose whether I take a CT scan, you know, for the patient. So it also affects how the YN maps to ZN as well. So that's kind of the action. You can forget about the generative model. It's just simply a mapping of, you know, the variation or relationship across the board, all right? But one thing that we need in this model is how we transition to the next stage, right? Conditioned on all these other variables, like the past state plus my agent variables, okay? To simplify the notation, here's what I'm going to do, okay? To simplify the notation, I'm going to use a vector S to denote the agent variables. So my agent variables are A, Y, and Z, okay? So they're going to be summarized under S. And I'm going to drop the Markov condition because it may become confusing when you have X on the left and the right side. The difference is on the right side in the condition, you have the previous X because of the Markovianity I put this, but let's ignore it for the simplicity of notation. So I'm going to simply be using the distribution of my next state given the agent variables, okay, just to simplify the notation. So let's move on and make some initial definitions, moving on to active inference. So what we need, again, as I said, is this transitionary distribution. What I typically have with my data is the joint distribution. So how do I have it? For example, as I shall be talking, hopefully if time permits, we have access to cancer treatment data. We just basically put all these variables together and come up with a joint distribution after normalizing the variables. And it can be thought of as, like, geometrically a state dimension. Let's assume it's one-dimensional, and an agent dimension. It's multi-dimensional, but in this figure, I'm summarizing it as one dimension as well. And everything that I measure pertaining to the state and the agent is in this very complex region, all right? So the dilemma is, it's a very complex region, many, many dimensions, depending on the agent, how many agent variables that I have, and how many state variables I have. And to move from the data that I have to the transitionary distribution, which I call P-base, I need to integrate in this region for a given S, for example, I need to integrate out from, you know, like in this region for all the X variables, which is in the continuous world, very, very complex. And you don't want to do that. Even in the discrete world, it's complex for a variety of reasons. I don't want to get into those reasons. It eliminates the recursive nature of the algorithms. I can talk later about that if you have questions. But let's, for the time being, take my word for moving from P data to P base being very complex, both in the continuous and discrete world, okay? So here is what you guys do in active inference. You instead define a variational distribution, Q, It's kind of an approximation to my transitionary distribution, which I call P base, all right? And, the objective is to be able to do A, my, inference, B, my control on this new distribution, this new quote unquote approximate distribution, okay? So the question is, how do we manage this? And how does this whole dynamic look like? Okay, so that's the next question. But let's remember P base is transitionary, P data is the joint, okay? So one quick, immediate, thing, derivation, very basic derivation is, again, I said Q is the variational density. I wanted to approximate the transitionary density closely, or the distribution closely. So one natural thing to look at is the KL distance. D represents the KL distance. I'm going to explain why it's natural in the next slide. All right. So this first term is the definition of it. Okay. So Q log Q over P base is the definition. And here what I do is I add a log of P agent and subtract the log of P agent from this expression. All right. And when I combine P agent and P base, the product gives me the data distribution. So I rewrite this D, which I want to be small, preferably 0, as the combination of these two terms, okay? So this first term in this summation is nothing but the KL distance between Q and this time the joint distribution, the data that I have access to, okay? Plus the log of P of the agent for the associated agent variables, okay? So this first term is referred to as the variational free energy, F. One very important thing to notice is a function of the agent variables. And the second term is referred to as the surprise. It's also a function of the agent variables. So if I put this inside of the geometry, all right, which I will dig deeper in a second, one thing that you should notice is this surprise is for any given S, for example, for any given set of agent variables, it's basically integrate out your state variable, which means like the weight of this line inside of this surface, all right? It's called the surprise. So for a given, set of variables, surprise changes as a function of the agent variables, okay? And they need to add to 1 because it's a well-defined probability, all right? So let's move on. And from this basic definitions, let's get a few immediate observations, all right? Let's get that. So first off, the observation is these are distance metrics, so they are necessarily non-negative, but preferably like this thing is 0, but they're necessarily non-negative, which means this right side is non-negative, and immediately it implies that the variation of free energy is lower bounded by the surprise, all right? So if I take this expression and make the agent variables random instead of specific and take the expectation of both sides, I get an expression for the expected free energy, which then turns out to be lower bounded by the entropy of the agent side variables or the agent variables. This is very important. This is one of the, in the future, I'm going to be using this inequality, but this has an implication. So H of S is the amount of information that the agent contains about how the system, everything about the system. This is the information that the agent has, and expected free energy is an upper bound on. It's going to be important later, okay? One other reshuffling of the terms leads to a really cute expression as well. Free energy, this is the expression that I have. I can break it into 2 in a different way. And the first term is the cross entropy between Q and P data this time, okay? So Q is my variational distribution, the guesstimate of the transitionary distribution, and my P data is the cross entropy. minus the entropy of the variational information. So this has, I think, the implication that indeed, when we say free energy, we mean free energy. Physically, we mean free energy. Why? Because like within a normalization factor, I can view this cross entropy as an energy term. I mean, it's referred to as Laplace encoded in energy. And entropy is entropy, okay? And I can convert everything in with a, say, Boltzmann constant factor within the energy, unit of energy. So this is indeed referred to as free energy, means free energy, all right? And it also has predictive coding implication. You know, you can think of the free energy as the number of bits wasted for encoding, you know, a source, a random source using distribution P data, all right, instead of using distribution Q. So there's like a predictive coding implication, which I don't want to spend too much time on, but later on, if there are questions, I can dig deeper into this, all right? So this was the setup. Now let me come into a few next stage, you know, introduction, going back to the dynamical systems, okay? So it's kind of the important part of the block diagram that I put together. So one very important and very interesting thing about free energy is it's not only a function of your distribution Q, variational distribution, but also your action and perception. So your action and perception also shapes the variational, the free energy, okay? So, for example, if I want to optimize for a given action, if I want to optimize my perception, you know, to minimize, I'm going to explain why I want to minimize the free energy in a second. But if I want to minimize the free energy, okay, simply an optimization problem across the perception variable of the free energy, all right? And likewise, I mean, because the time from the system state and the sensory variable is instantaneous, I use the variational free energy, all right? So the second alternative is, you know, I can optimize the free energy in this across the set of, you know, the agents, the actions, all right, that I take. But this time from the action to the system state, there's a unit delay. So it's preferable that we use the expected free energy, which is simply take the expectation of your variational free energy to reflect it or to project it into the next stage. So I'm taking the expectation over the Q of my next stage, all right? And, you know, here, the important thing is I'm minimizing the free energy across my actions to achieve a specific goal. And that specific goal, as we shall see, is a combination of multitude of things. One of them is not, you know, it's typically one would think that it's just the inference, as the name active inference implies, but it also is pertaining to the actions to take to draw the system state to a desired end state, which is something we will be talking about in a second as well. So that's one of the more interesting things about the free energy interpretation. Let's get a little more intuition why these optimizations are interesting, all right? So to that end, I'm going to use information geometry, all right? So information geometry, simply I'm taking the set of states and breaking them up into these dimensions, all right? So these are the possible values or the number of different values that X can take. Suppose it's discrete and it can take on 3 possible values. Then on this simplex, I have the set of possible distributions for X, all right? So it's a simplex, it's a 2-dimensional simplex. And for everything else, suppose if I look at the distributions for all possible values of the perception variable, it's a subset of this simplex, all right? So this optimization means I simply take my, so Q, my Q variable, variational density is nothing but a point in this space, right? And what I want to do is I want to look at across all possible perceptions, the perception that minimizes the distance to the KL divergence to this Q. And this is, in fact, what I do visually when I optimize my perception. Likewise, I mean, okay, when I do that, this distance here turns out to be the minimum free energy, okay? So it becomes a distance in this geometry. Similarly, if I do the same for the action space, what I call the action space is a subset of this simplex, all right? And optimizing in the action space is similarly minimizing the distance from my variational distribution to the action space. So choose the P that's closest to this over your set of actions. So that's the interesting thing. I'm minimizing over the set of actions. So as I vary the actions, the values that I take, the distributions that I'm looking at is across the set of actions. So that's very interesting and has a few implications. And I'm going to give those implications in a few examples that I think are relevant here. All right. So again, take the same probability simplex. Again, simplifying assumption, X takes on 3 possible values. So when I want to move my arm, here's what I supposedly do or can do. All right. So this is an explanation of what I'm doing. And it's a great explanation, in my opinion. So instead of taking the action, first, I map my perception to, like at time n, if I want to move my arm, to a desired perception, which is where I want my arm to be in the next state, right? So this is what I do first, rather than like causally moving from action to the perception. I want to move from perception to the action in this stage, okay? So if I look at, for this desired Z set of perception, if I look at the viable actions, it's in a subset, all right? So what I simply do is I minimize the action, meaning I minimize the free energy between my current variational density to, I find the closest point among the set of actions, among the set of distributions. I pick the action that gives me the closest point within this subset, okay? So, and I take the action accordingly. And for example, if this action is not sufficient to move, to make the entire move, and I end up with somewhere in between, I rinse and repeat. I keep repeating with the observation. I update my perception. I set the desired perception again, and I update in time n+2 accordingly, if I have higher time resolution, for example. Again, another example, which is, again, my way of interpreting how things are working here. Suppose I am leaning toward conspiracy theories, then in my opinion, what it entails is, in this subset of set of perceptions, the entire subset encapsulated by the dashed boundary, okay? I'm limiting myself to a subset of a smaller perception space, which is a subset of the entire possible perceptions that I have. So it's kind of where I'm limiting myself to. So when I make an observation, which is outside of my control, say something happens in the world, my interpretation for it is not going to be hey, the world is actually P that's closest within the entire set of perceptions. But because I'm limiting myself to this subset, I'm saying, hey, my perception here, Zn star, is actually the closest point within this subset. So it's kind of a suboptimal solution. But because I constrain myself to this subset, that's what I solve in my brain. This minimum energy problem is the one that I solve in my brain to interpret, which is basically finding the best perception, all right, the events that are happening. So these are just very interesting consequences of free energy being not just a function of variational density, but also my action and perception. So I'm basically in this framework moving the causal direction from one to another freely, which I could do because of the relationships that I have defined in the first slide. Okay, so this was kind of a very long introduction and some, the way that I perceive things. One quick break here before I move on to the next step is like a quick, I don't want to call it criticism, but an alternative proposal. So free energy is defined as a distance. It's defined as a KL distance, okay? So if you look at the KL distance, it is great, turns out to be great. Why? Because free energy has the physical significance. Free energy indeed means free energy, and it has a physical significance, a physical mean, right? So that's great that I define it as a KL distance. But if I dig deeper, KL distance, has a very high weight. If I look at the distance between my variational distribution and my real world, for example, data, all right? So it favors shifts at the center way more than shifts in the tail. So the tails are suppressed quite a bit in KL divergence. Just to give you an example, if I shift the center of a distribution, the energy, the KL distance turns out to be 0.5, for example. If I add like a weight, 5% weight to the tails, which is not insignificant, all right? It's an order of magnitude lower. So, here's one potential consequence of this. If, this slight shift in, for example, mean, if I interpret it as a regular day, some slight anomaly, like I cannot find my shoes in the place that I leave them, all right? So if I interpret it that way, and if I interpret this tail as, I open the door, I see a tiger making a run at me, which is very unlikely, like a deviation, all right? So if both of them happen simultaneously, there's a disproportionate weight on me not finding my shoes, all right? So again, if a naive interpretation of this, favoritism is, I would be much more inclined toward looking for my shoes versus making a run away or addressing the tiger issue, because the free energy is dominated by the shifts in the center compared to the tail variations. So I'm sure Magnus has a better explanation of this and explanation of why this is not an issue. But having said that, I still want to go ahead and propose a few alternate ways of looking at it. For example, Renyi divergence is a generalized version of KL divergence. Maybe we can propose for certain tasks using the Renyi divergence instead of KL divergence, and I can adjust the how much priority I want to put on the tails versus the mean. Or alternative, another naive approach would be a survival weighted version of KL divergence. I put the survival function next to my variational divergence, and I optimize with respect to both combined. All right. So this was a small break, and I want to move on to an implication in the dynamical systems. In the interest of time, I want to spend a short amount of time and I give the result. This is one of those situations where I think the result is more interesting than the derivation itself, even though the derivation has some subtle expressions in mutual information, which is going to be important as you do math in dynamical systems, okay? So here's what I did. What I did was I take the dynamical system and compared the entropy of the state of the system in an open loop system, which means I don't have feedback. I don't have this perception and, action accordingly. versus the closed loop, which means I have the action and perception. So the agent is actively acting here. And in the open loop, there's no agent acting. I'm just simply, the controller is blind, simply controlling the system without the agent being in there, okay? So what I did was, I looked at the difference between the entropy of the state in these two cases. Why is it important? Because controlling means, in some sense, lowering the entropy. If I'm controlling a system well, it means I have a lower entropy of the state given the information that I have. That's what, in a sense, control means, right? And when you do the math, it turns out that the difference is identical to some mutual information, which in turn is upper bounded by the entropy of my state, my agent variables. This is instantaneous difference at time n, the entropy of the agent variables given the past state, okay? So this is instantaneous. But we just derived that. This is like an upper bound. Upper bound for this is free energy. So why is this significant? This is significant because what I'm stating, what I'm calculating here is a validation of second law of thermodynamics. What I'm saying is the amount of entropy that you can reduce at an instant n is no more than the amount of information that you have about the system. Indeed, I mean, if I don't have enough information, I cannot reduce the entropy at the same rate. So this is literally the second law of thermodynamics stated in dynamical systems. And what you have in free energy is another interpretation of the second law of thermodynamics. The instantaneous drop is in entropy is upper bounded by the expected free energy. Okay, so that's kind of a deep consequences. If you take this one step further and add it across the board, which means I'm going to look at the accumulation of reduction in entropy. It's the accumulation in, the mutual information, which reduces to directed information. So as a consequence, the sum of free energies across the board, or the accumulation of free energies, is nothing but a causal information flow from the controls of the system to the state, all right? So I'm going to, again, not dig deeper further into this, but there are some very interesting consequences, which I cannot claim I have covered all myself, because I'm relatively new to the area. But a few of these thoughts for discussion of the implications of the statement that I just made is, you can add age of information and sampling regularity to maximize the reduction in entropy, to minimize the free energy, expected free energy. And one interesting result is you do not necessarily need to sample regularly to achieve the minimum free energy. So some irregularity there may even be better, some randomness there, okay? I can also talk about, in case of interest, conditional entropy and Maxwell's demon, and some information theoretic definitions for complexity later on. These are all deep topics that I am very excited about. One last thing to wrap up, maybe, hopefully I'm gonna spend 10 more minutes here and wrap up. I was very excited, so I applied at, an early application of all of these insights to a problem in cancer treatment, all right? So here's the problem. I want to find personalized treatment strategies in a simplified cancer treatment problem, and I want to minimize the tumor size, but there are a few constraints that I have to make it aligned with the problem that I'm looking at. First off, I want to minimize or control the dosage of medication that I'm using, and I have a budget on measurements. So I can't draw blood every other hour from the patient. I cannot take a CT scan every day from the patient. Those are like subjected to budgets, and I want to pick them very carefully, all right, to meet a budget. All right, so here's the mapping to the problem. Let me start on the right side, okay? So here's the state. I mean, so the evolution is the same as the figure that I except a little more simplified of the state of the dynamical system figure that I drew. Okay, so here X is two things, but focus on X being the tumor size, all right? But I also add another like probability of an emergency room visit. It's kind of if you make it more complex, like a two-dimensional problem, right? But it's the tumor size, basically in a nutshell. So you have an observation, okay, which may be merely nothing, okay, blank, or you may have an observation that the patient just visited the ER room, or it may be just, hey, I ordered the CT scan, all right? The action is basically order a CT scan and also choose a specific dose for chemo, right? So that's my action. So my action also affects my observation variable Y here, okay? And I have the evolution. So you may be asking, hey, what the heck is this theta on the left? That is patient-specific variable. It's a non-ergodic variable. It doesn't change. It's basically, I'm implying that there's like a patient, for example, age of the patient, early stage versus late stage. Okay, so it's kind of agent-related, patient-related variable that is an overarching variable that also affects the transitions. So not all patients are the same, and they are specified by this variable theta, okay? Here are kind of some of the details. One last thing, maybe I don't want to add already, it's very notation heavy presentation. I don't want to keep adding, but one more thing that you should maybe think about is these medical observations. There's an indicator variable. It is equal to 1 if I order imaging. It's equal to 0 if I don't order imaging, for example. It's kind of the indicator variable, which may be important later on, okay? So, all right. So here's the problem statement here. We want to minimize the tumor state, all right? Expected tumor state over the course of the treatment, which is N. N is the time for the, the course of the treatment. Please, I mean, there's like a typo K, not T. Please change this as K. Subject to a combination of the dosage that you use and subject to an expected budget on the imaging that I have, okay? And this turns out to be a constrained POMDP. Instead of using classical tools to solve POMDP, what I'm going to do is I want to apply active inference here, and I want to apply a variation of active inference. So use the ideas, apply a variation of active inference in my solution. So here's the caveat. I promised I don't want to add more notation, but here's what's coming. Sorry about this. Let me explain what I'm doing here, okay? So you don't have to follow line by line. Here's what I'm doing here. I just threw everything in the slide and in the next slide, but here's what I'm doing here. Step 1, I am using variational free energy, but instead of plugging Y, my observation, my agent variable in the current time, I'm projecting to the next time, okay? Projecting to the next time. So it's like N, instead of N, I'm using N plus 1, but it's a definition, so I just use it, all right? Second step, this is still variational free energy. I take the expectation of both sides over the observation or projected observation given my action, okay? Over the projected observation given my action, which means my expected free energy is no longer a function of my perception or my observation, but it's only a function of my action, okay? So the expected free energy naturally gives you a framework to act on the actions, okay? And a few complicated operations breaking, like factorizing the joint distribution of Y and X. This is your, state and observation variables, and also adding and subtracting Q of this projection to the next stage given the action. You break your expected free energy into 3 terms. I'm going to talk about these 3 terms in a second. But here's, to me, the most interesting and weird step, which is one of the main values of active inference in my limited perspective. Okay, so I do this thing called preference substitution. So I take this actual probability of the next stage given my action, and I replace it with a preferred distribution. Okay, it's weird that I can freely do this because it's not like my Q function. It's my P, the actual P. But what's happening is when I do this, my problem, the only reason I can do this is if my problem aligns with this and eventually I have some sort of convergence to this preferred distribution. If I don't have a convergence, then this step would not be correct, all right? So if you, again, going back to this division of the 3 terms, what you see is this division is a very natural interpretation of free energy. So I have a risk term, all right? A risk term, which is basically the divergence, this time between my variational distribution and the preferred state. So it's kind of the distance from the desired state. I indeed want to keep this small because I want to converge to the desired state. And another term, this time mutual information between the state and my observation. I want to maximize this, all right? This is the second term. And the third term is more complex, but ambiguity. This is like has the it's kind of observation uncertainty given the dynamics. This also has this coding perspective. I want this to be small as well, right? So I want Q to be closer to the actual distribution. So indeed, I want to find a balance between these 3 terms in my optimization, all right? And that's what minimization of free energy does. And if everything works fine, indeed, this distance term is minimized and convergence to P-pref will happen. But by me freely replacing the actual distribution with the preferred distribution, okay? So here's what I do. I don't directly solve this problem, but I want a simple version of it. All right, so there's Magnus' question coming. What is H in the ambiguity term? Should I read this as a divergence between entropy and Py? So, okay, yeah, so this is what happens when you put all this algebra heavy notation and don't explain it, which is a great question. So this H term is cross entropy. It's cross entropy between Q and P. It's defined as Q or minus, summation over this Q minus log P, okay? So it's basically how many bits I use to encode a source with distribution Q using as if the distribution is P, all right? And that's basically the entropy plus the free energy, all right? And I'm taking the expectation on this. The smaller, the better, which means the closer my Q to my P, the better, okay? So again, I'm not sure, Magnus, if I explained this clearly, but, maybe we can revisit this after the session or in the Q&A session. All right, thanks for asking that. I'm not solving that problem. It's way too complex to begin with, at least. So I'm basically taking that as a motivation and slightly modify the terms. For the information gain, that mutual information, I'm replacing with my expected indicator variable, okay? For the ambiguity term, instead of using that cross entropy, I'm using the entropy of the state given my observations, my action agent variables. And instead of the risk being the divergence between Q and P pref, I'm using Jensen-Shannon divergence. Why? Because it's easier to handle. And one other thing that I'm doing, right? I don't want to constrain myself for these 3 terms to have identical weights, all right? Which is maybe something that we can do in free energy minimization as well. So I freely added variables. I want to adjust the weights or the importance of these different terms. So I added weights C1 and C2 here, all right? And I still have the constraint on dosage, but I don't have the constraint on my measurement budget, because I'm directly injecting it into the cost function here. All right. And I'm going to now apply this problem on an actual data set. We are using a data set from AACR. It's a American Association on Cancer Research. They have a very nice data set, patient-level data set. And there are many, many data sets that you can correlate across a patient, okay? Long story short, what we have done is we have taken an actual data set, all right? And we have defined states. These are what we defined. So we have defined, for sake of simplicity, 4 possible values for your X, okay? It's improving, responding, stable, no change, progressing, worsening, in the order of good to bad, and, not stated intermediate. Okay, so so these are the 4 states that we have defined. And we have also included the terminal state of death into the data. And our categories, the theta variable, has 6 different variations. It's basically elderly patient, middle patient, young patient, and advanced stage and early stage. So there are, across these 2 different dimensions, we have 6 different values for the patient category, right? These are the number of data points that we have. And our action is, there are 7 different potential action spaces that you can use. And we have focused on chemo, and there's like more than 1,200 data points that we can use in our work here. And from the data set, we have generated the transition probabilities. As an example, I'm presenting 2 of them from the states, okay? It's like the early stage. The top states are good states, stable, progressing, getting worse, and death as the 4 states. So these are the transition probabilities if your action is do nothing, okay? It's not like stand still or before the patient even shows up, all right? This is what happens. And the same transition probabilities with chemo, all right? And I'm focusing on the early stage, middle age category. Just to get some insights, focus on this below diagonal points. These are the transition probabilities from the bad states to the good state. So I want these probabilities to be high, okay? These probabilities to be high. Without chemo, they're kind of low. With chemo, they're also not super high, but still they're like doubled or tripled, right? So for example, from progressing disease to a stable disease, here there's a very, very little chance, but it's tripled, doubled with chemo in the early stage patients. So that's how you should be interpreting these actions. So here's what we did. We basically applied a naive solution. So rather than the full solution, we first looked at all the possible preferred matrices. So this time, because we have a discrete set of potential matrices for patients, we picked them and we basically found the preferred matrix using a preferred state distribution and inverting it using this algorithm called Metropolis Hastings, okay? So now we have from preferred state a set of preferred matrices. And here's what we did for the observations. We observed if the entropy associated my variational density is over something. So I don't want the entropy to go way above a specific threshold. And lastly, this is kind of a bit complicated, but how we chose the action or the dose is we still assumed, again, this is kind of a toy assumption, but we assume we don't know the patient category. So we assume they're unknown, and we are kind of trying to estimate them as we treat the patients, right? As a result, there's like a posterior distribution on the agent types. And for each one, there's like a direction that I want to move for the preferred state or the preferred matrix, all right? So we basically take a weighted average of those directions based, I mean, the weights being my guesstimate or my, posterior distribution of what I think the category of the patient is. All right, so that's what we do. And here's the result. I promise this is the last slide. These are simulations, but these simulations are smart simulations because they are kind of all the weights, transition probabilities, and all the transitions are chosen based on actual data. But at the end of the day, these are like using those parameters, these are like simulations, okay? So it's kind of state transition over time, all right? And, here I would like to start with the agent belief, entropy over time, all right? So again, my rule for observation is entropy is above a state I observe. So as you can see, I take imaging for a long period of time, successive imagings, but as I keep narrowing down on the category of the patient, it goes below the threshold, and I, you make it more sparse. My observations are more and more sparse as my entropy keeps below this threshold, okay? Depending on your budget, you would choose your threshold higher or lower, okay? So that's how you control your budget. And agent category, as I take more and more observations with the actions that I take, one of the categories, I'm not showing all the category beliefs, but my category belief evolves in such a way that I pretty much narrow down on the actual category, okay? And this is, I think, the cool thing. As you can see, as I keep taking these steps, as I apply these steps, the distribution, desired state distribution converges to, the actual steady state distribution converges to my desired steady state distribution, okay? So shown here. So this is where I would like to stop, and happy to take questions at this stage. I'm a bit over time. I apologize for that.
Thank you, Emre, for this fantastic tour de force. Let's all unmute and uncave ourselves and give Emre a round of applause. Thank you.
Thanks, I appreciate it. Yeah.
No worries for going over time. It's all good.
Yeah, I'm new to the area, so it's only build. I mean, I'm super excited to be collaborating with every one of you guys. So as to take this further.
Excellent. So now we open the Q&A session. Are there anyone have any question?
So I have something that I'd like to bring up. I apologize. I missed part of the earlier parts of the talk because I had to do some work on the other screen. But at some point you derive the expected free energy, you derive a bound on that. I think it was bounded by the mutual information.
Yes. Oh, are you talking about this expected free energy? Well,
I had somewhere where you had the change in.
All right, got it. So it's not at the earlier stage, but it's like in the.
Yeah, because this is one of the things I managed to pick up when, after I had time to tune in again.
I think you're referring to this. So the change.
Yeah, this thing.
Open loop and closed loop, the amount of entropy reduction difference is identical to the mutual information between the state and your agent variables given the past state.
Yes. So I think the way I would usually go about deriving the expected free energy would be in terms of a KL divergence and a mutual information term. So I think this bound is getting at the same thing. Like the difference between the two would be exactly the KL divergence that's missing from here.
Very, very nice and interesting observation. So here I put, there are two bounds here. So one of them is, mutual information is the difference between the two. Yeah. But if you look at the second term, if I know the current state, if I know the next state, and I'm taking the actions and I'm like the agent, if I know all of this, my claim is that I can pretty much narrow down on what action I have taken with these two information. If my action is deterministic, I mean, if I'm taking a bunch of random actions, maybe this is not true. But if my action space are pretty much deterministic or close to being deterministic, this second term will be very close to zero or identical to zero, right?
Yeah, then you get this bound.
Yeah, it is a bound, but it's a tight bound if my actions are deterministic, okay? And likewise, if my actions are deterministic, the cool thing is, earlier on, we derived an upper bound or even an exact expression, again, with the same assumption, that this guy is equal to the expected, like my surprise, right? My surprise is, upper bounded by expected free energy, or the entropy is upper bounded by the expected free energy. So, these bounds are, in many instances tight. And what I'm claiming is this entropy reduction is tightened by the expected free energy. I haven't thought further about this, as it pertains to free energy, but there is something here, in my opinion.
Yeah, definitely. I just wanted to flag that I see the same kind of thing. And if we decompose this in a different way, we might be able to get the terms even nicer. So I really like this part.
Let's do it. Let's meet.
Yeah, absolutely.
In our meeting.
The other thing that I noted down is the same thing that we talked about on Monday, where you have this comparison in the tails. Yeah, this one.
Yeah,
Where I
explain.
think, yes, I think there might be a different interpretation, which is there's a sort of a model comparison problem in disguise going on here, because you change P quite a lot between the two. So in terms of just comparing the free energy, I wouldn't say this is necessarily a fair comparison, because the model that you're computing the free energy with respect to is quite different. One is just a Gaussian, and the other one is this mixture that you have written out for P2.
So I thought about it. You're right. I mean, I totally understood what your concern on Monday, but again, I still chose to put this slide because, I mean, it's still categorically true that the KL divergence favors the different differences at the center compared to the differences at the tail. So that may be, again, maybe not, maybe you have even a deeper explanation for that. But if there are two things that are happening, two deviations that are happening, one at the center, more casual difference. I gave the example of me not finding my shoes as I opened the door. This is me seeing a tiger, which is like a 3, 4, 5, 6 standard deviation away from the normal. If I'm minimizing the free energy, I would be favoring I would be putting much higher weight on finding my shoe first, which is maybe something you don't want to do in certain situations, right? So I was kind of offering alternate, ways of looking at the problem. Like, I mean, we use Renyi divergence, not significantly different, but slightly different. Like Renyi divergence is a more general version of KL divergence. If you choose alpha to be 1, it's KL divergence. If you choose alpha to be 2, it's much heavier weight on the tails compared to the center, for example. Or even a more intuitive one, survival weighted KL divergence. I put this S function in front of Q here so that I have I correct for what I care about.
So yeah, I think my response to that is that besides the difference in models, this version you've built also has a mismatch in the family of Qs and Ps you're considering.
Oh yeah.
Like for basically, because if you know your P, your generative model has 3 peaks, and you're trying to model it with 1. Then like that is going to lead to a poor fit. Absolutely. So I think there might be something to how to work with tail events, and if you want to favor them. But I would probably do it in a way where like we nuance the match between the models here, because there are a couple of things built into this that just makes one of the models have a poorer fit, sort of by design.
Mhm.
That I know, like Noor did some work on Renyi divergences and the like, but in general, I would see if my first intuition for thing to try with this would be to say, if we build the Q and the P so that they match and we sort of go through all the motions very, very meticulously, does it recover this sort of tail covering behavior, or does it still have issues? And my hunch is that if we make a match, we should be able to recover these. But that is,
Right. Sure.
again, not something I've tested.
Let's look at, actually, that's a great question. That's a great problem. So you put, I mean, the tiger is one example, but you put all these tails, right? I mean, that you can think of, which is written in hardware in me of different events, like that I react to with priority, and see if there are all these bumps, all right, how I react. And in fact, that also leads to a perhaps even a more interesting question, Magnus. What if I don't, evolution didn't put certain things in my wiring, like, hey, I have something for the snake, for the tiger, I have different actions for all of these, but I don't have something for aliens, right? So what if it's not there? And maybe my action is, as a result, not as, extreme as if I have seen the timing. So what is the difference between, so maybe my example here, the mismatch, the unfair mismatch, is pointing to seeing aliens, because my base model is never geared towards seeing an alien, but all of a sudden there's like this really tiny weight on the tail for the aliens. So maybe that's I don't react. Maybe that's why I'm kind of suppressing these actions, because I've never seen it, and my wiring is never built by evolution to react to aliens.
Yeah, I think there's definitely something here to be explored. Like, how do we deal with tail events that are unlikely under the model, and whether that requires, like some model expansion tricks or some model comparison tricks. I'm not sure what the best way to go about it is, but yeah, I want to flag that I think looking at this is probably something that's going to be useful. I'm not sure whether Carl is going to shoot my suggestion down in another 10 minutes, but fingers crossed. I think there might be something here. Like the third, I basically wrote down 4 points when I took notes. The third thing I sort of caught onto is something you did sort of offhandedly, where you started to minimize EFE subject to constraints.
Right. So
I think it was later.
So in this problem, I guess, right?
Yeah, these kind of things. Where you say, I want to minimize the expected free energy subject to the constraint that XYZ, like something, some costs didn't add up. Yeah, so these kind of things.
In the problem definition, it's, here I don't have EFE. Here I have the core problem.
Okay. But just this idea of trying to explore the role of constraints in active inference, because it has been done in terms of adding like strong priors and C vectors and these kind of things, but being explicit about modeling the constraints sort of in general, I think is also something that at least I haven't seen particularly well explored.
So indeed, I think that's what you need to do with limited information. Indeed, so this is not the problem. It's not, you don't see expected free energy here, but I put 3 terms that I can readily calculate with the exact same motivation that I built from the expected free energy. Like, I replaced these 3 terms with other 3 terms that are relevant, but not identical. And indeed, there's a constraint. And this is what we do with limited information or with limited constraints. You need to solve that problem, minimize expected free energy subject to certain constraints.
But I think putting them in, sorry, you go. I did want to explain.
I want to even take it a step further. So, the expected free energy kind of naturally breaks down into these 3 terms: risk, information gain, and ambiguity terms, right? These 3 terms. And indeed, minimizing all of the three make sense, but I don't have any coefficient. I mean, this expression does not have any priority of one over the other. Maybe I want to have a higher weight on the mutual information. I want to do inference. I want to learn it very quickly. That's my objective. Versus maybe I want to have a faster convergence to the preferred distribution. So one way that this is, I mean, for lack of a better word, limiting is I don't have coefficients controlling the weights of these three different objectives. All right. So basically taking a sum of them, minimizing it, which makes sense, but maybe I need a coefficient in front of these terms so that I control what is more important for me. And to your point, one way of doing it is using constraints. For example, if I say minimize this divergence, the first part of the expected free energy, subject to a constraint on mutual information, this form is literally the relaxed version, Lagrangian relaxed version of that constraint optimization problem, where instead of the Lagrange multiplier, I put unit one unit. Okay.
Yeah.
So why not put lambda here? Like, I mean, so it's another, exactly as you said, maybe we should look at it as, hey, take one of the terms and minimize that subject to constraint on the other terms.
Yeah. Again, I think the standard way I would go about this would be to mess with the priors in the model, but making it explicit like you're suggesting, I think there's potentially some really cool stuff to be done there.
Yeah.
Yeah. And the final thing is that I think the way you went about the optimization is also different to most of the sort of planning algorithms I've seen for working with expected free energy. So just in terms of exploring that and seeing how the different methods compare, I think is also going to be a useful exercise.
Yeah. I mean, exactly. So expected free, the way I did it, so I apologize, like a toy simplification. I could calculate these, so why not? The reason why I was motivated to do this was I felt like active inference, like free energy minimization, has that flexibility. I mean, the way people use it is very different. I mean, they have the flexibility. For example, what is mind-opening to me, and I keep saying this, but what's mind-opening to me is I am minimizing my free energy over the set of actions. As an example, I take the action that gives me the best inference. It's almost like the opposite of what we do in engineering. I mean, there is certain best fit to your data. You should take that best fit first before you do anything else. And with that best fit, choose the optimal action. But what this free energy work says is that, no, do them together. I mean, you may even take an action that fits the best perception, you know, like, or even take the causal direction differently, take the perception first. Like, I mean, imagine that you're moving your arm here, and then minimization of energy over the action space is, now that I thought about it, the minimum free energy is if I take that action, indeed. So it's kind of an experiment. Again, I'm not by no means in neuroscience. I have no understanding of it, but it's another explanation of perhaps what's happening in reality, you know, so.
I agree. I think this, like, obviously I'm biased because I think this is the right way to do things. But yes, indeed, turning the action selection problem into an inference problem, I think, is a really, really neat insight. Because again, by extension, it also means we can solve it as if we're solving an inference problem.
Yeah, exactly.
Which is a whole different set of tools. Because now I'm not necessarily in the world of control theory. I'm in the world of doing inference.
Yeah. What free energy principle is saying is that those are same problems.
Yeah.
Inference and the action selection problem are the same problems. So that's what's cool about it. I don't have to worry about them about the separation or, hey, how much do I?
It's just inference.
On mine, it works, right? So that's really nice. And I'm making all these statements with Carlos here, so I'm potentially embarrassing myself at this stage as I'm speaking. So, yeah.
Again, I don't have any other notes. So But yeah, I would also really like to hear from Carl what his take on all this is.
Thank you, Magnus. Before hearing from Carl, are there any other questions from the audience? If not, maybe I can venture one, because I was targeting precisely these slides that we are on now. And I think it's related to what Magnus asked. And I think what I would like to more now, I mean, now I have more context about why you did what you did, but I'm curious, which are the, KL terms in the original VFE or EFE are replaced here by the JSD, and what is and what is the explicit optimization objective?
Sure.
And also maybe, and this just to ask all the questions, how this change using GSD change the tail sensitivity that you mentioned in the beginning, that was a fault in the KL.
Very, very good questions. Very good. I mean, some of the answers that I don't know, but let me go one by one over these terms and what I changed here. So first, let's look at, as you said, this divergence, KL divergence between Q, variational distribution, and the preferred distribution. I changed it to JSD. JSD is basically the average of two distances. Just think of it as the average of two distances. So there's this preferred distribution, and then there's your Q. KL divergence looks at the KL divergence between those 2 points. JSD, what it does is it picks the midpoint, literally takes the average of these two distributions and picks the midpoint, and looks at the average between from one to the midpoint, from the midpoint to the next, divided by 2. So looks at the average distribution. For a certain reason, it's more analytically tractable, in derivations. That's the only reason why I used it. And what I don't know is, I don't know whether this would solve that tail question that I brought up. So I don't know about that. So the second mapping, which is like, hey, one of the terms is information gain. So like the mutual, when I take this action AN, what does it do to the mutual information in the next stage between my state and my observation, right? I want this to be high, right? Because I want to get good inference of the actual state. I replace this with, again, very naively, with this expected indicator variable, which is, in my problem, refers to observe the patient. So when I observe the patient, the mutual information is really high, right? I mean, so I get almost like full mutual information. When I don't observe the patient, I get 0, which is kind of reflective of that mutual information, because if I don't observe it, my y doesn't exist, yn plus 1. So it becomes 0. And when I observe it, it's high, right? The mutual, because I can assume that I have a very good, precise measurement of the tumor when I take a, CT scan or something. So that's why this binary variable made sense. It's also kind of simple. And lastly, the ambiguity term is here very complicated, this cross entropy term. I replaced this with an actual entropy term of the next state, given my action and my observation. So it's the ambiguity of if this drops, it means I am taking all these actions, but I don't know what the state is going to be. It's like really uncertain, right, in the next state. So maybe it's a good idea to make an observation at that point. So that's kind of the analogous to ambiguity in the previous slide.
I see. Yeah, okay. I think I get it. Just one extra clarification for the information gain term again. So if we go back to the previous slide, so it's the mutual information of X and Y, joint X and Y, given actions. But in your case with the patient, when you can't observe the tumor, so future evolution of patient state, when you can observe the tumor and do any sampling of the patient, mutual information is high. But then what is the action space like when you can't observe the tumor? What?
That's a very good question. So the actions, so when I can, I made it sound like when I don't observe, it's completely blind, but it's not true. So I use my previous observation. So the mutual informed, let me show rather than expressions, let me show the results. When I don't observe the patient, the mutual information doesn't like jump to, or the entropy doesn't jump to a high level. It kind of slowly increases, right? I mean, it goes down. I observe, it goes down. I don't observe, it goes up by a bit because I still have the previous observation and I have still a projection on how it's going to evolve because I took the CT scan last week and I kind of applied chemo this week. So I still have a guess for how it's evolving. It's not like just because I didn't observe this week, my information is completely gone. Yeah. So it's a little, again, the way I explained it made it sound like it is, but it's not the case.
I see. Yeah. Okay. It's more clear at least now. Are there any other questions from the audience? So if not, something tells me it's Carl's turn now. Maybe the mutual information between my action and the future observation will be high now.
Implying it is actually my turn then.
Yeah, I am Carl.
Excellent. Thank you. Right. Where are we? Good. So I'm trying to see myself and I can't. Never mind. So excellent presentation and really interesting discussion. I think overall this this is, you know, in a very heartening way, very congruent with active inference. And if this has been derived in 7 weeks, then that's extremely impressive. The particular thing that I was impressed by, which I haven't seen so much in the particular application that was showcased at the end, was having these kind of bilateral actions. So one action is actually curative or therapeutic, intervening in the system, in this instance, in terms of the treatment of cancer. And on the other hand, epistemic in terms of information, your actions that are have implications for the way that you gather information. And to have both of these actions running concurrently in an active inference, optimal control planning as inference kind of context, I think that's a really important contribution that should be showcased. And your initial exposition of active inference, and in part really also a nod to the free energy principle and indeed earlier ideas such as those from cybernetics, regulator theorems, law of acquisite variety, and the like. I thought that was excellent. The comments that I would have are of two kinds. First, to endorse the key theoretical fundaments of the approach through joining the dots with papers that you have yet to read or possibly have read but haven't had time to digest. So I've got just a couple of papers, one of which has already been mentioned, which I think you will enjoy and will allow you to speculate on other directions of travel, and also, and a word which I quite often use, lend your arguments a construct validity, in the sense you can say there is another construct out there which is closely related, not identical, that reaches the same conclusion, and then you can refer to these other constructs. So I'll just briefly after I've introduced my comments, go through these papers and just explain why I think you would enjoy, there's only 2 or 3 of them, why you would enjoy reading them, simply as a way of justifying, motivating or validating the overall formulation in relation to other constructs that are very closely related, but they're all within the same church of active inference. And I repeat, you're at the end of your conversation, you were saying, you're not a psychologist or a biologist, and but you clearly know exactly what the ideas are, and a psychologist might call this perceptual control theory, where the control and the perception are just the same thing. An engineer in Bayesian statistics might call this planning as inference. So the planning becomes an inference problem, but they're all the same idea. And if you can make that clear in the way that you're explaining it, say to data scientists or control theoreticians, I think that will make your life much easier, and be another aspect of a useful contribution. The second set of comments is more about the technical details, and these are more critical in the sense that I think some of your derivations are slightly over-engineered, and you can tell a slightly simpler story, um, ironically, which makes your very last expression for the expected free energy, which you put together heuristically by borrowing certain terms from your derived form. In fact, your heuristic form is much closer to the expected free energy in the free energy principle than your derivations. Your derivations, I think, if you went through it slowly and just expanded everything in terms of log densities, a lot of those terms would cancel, and you would end up with something which was simpler. And what it would look like is, yeah. So those expressions, if you work through them, again, I haven't done what you have done, so I can't guarantee it. But my suspicion is that some of those terms will cancel, and you will end up with something that looks much more like the expression on the next page.
So
Yeah,
yeah,
this one here. Yeah.
very, very quick note on that. Very quick note on that. I normally do the opposite, as you said, like how can I simplify it? But this time I made an exception. So here, for example, if you look at it, we start with like a relatively simple form, and I didn't just plug it, but I added a term and subtracted a term. So there are like two extra terms here, so that I obtain like a mutual information term plus a cross entropy term, but maybe unnecessarily, as you said, maybe I don't
Oh,
need.
well, no. I think that sort of add subtract, I call this a sort of an inflationary device. That I think that inflationary device, which you also used to derive the variational free energy, is absolutely crucial.
They
And
call this the camel principle, Carl, if you want to have a name for it. I've seen it called the camel principle. So one camel plus a camel minus a camel is one camel.
You're right. Very good. Um, so it certainly has a role in deriving the expected free energy. My point is, based upon decades of deriving and rederiving the expected free energy, I'm almost certain that you will be able to eliminate many of these expressions, even having used the add subtract, or even having appealed to the Campbell principle. But the Campbell principle, read as Maxwell has just defined it, is exactly how you create these bounds and turn a marginalization problem into an optimization problem. And it also avoids you having to hand wave about Jensen's inequality and the way that usually these things are introduced. As I said, I can't confirm it, and I'm too old now to do it for you, but I can almost guarantee that you can eliminate a lot of these terms and get back to what you've got on the next page.
This one.
Yeah. Yeah, that's much closer to the expected free energy. When you derive the expected free energy from first principles. So I notice what you've done is taking the variation free energy and then taking an expectation under the posterior predictive density of yn plus 1. That's not quite how it's certainly, I think, a very sensible approach, and certainly taking the expectation under the posterior predictive density is why it is called expected free energy. Its derivation from first principles is slightly different, though. It is just basically deriving the probability distribution over action under a um, a steady state assumption that just is your preferred distribution. So it's basically saying, let's assume I've cured the patients to the extent that I can, and I'm going to write down that endpoint of therapy as a steady state distribution. And now, given what I know about um, the the dynamics probabilistically and the various likelihood mappings, the various mappings that you showed with the arrows, what is a probability distribution over A? And then you derive that. Um, and you express that log probability distribution over A as a potential, and it has the form of um, a relative entropy and a cross entropy, which is just a free energy, and that is exactly what you've got here. So the cross entropy now becomes your ambiguity. I know you've simplified it here to a certain extent by just picking a particular A and Y, but if you took the expectation of the entropy of the or in this instance, you've got your X's, which, yes, that's right. They're
I
the
think this is more like it. This term is more like it. So.
Yes, absolutely. Yes, that is exactly the ambiguity. That's how I read the ambiguity. That is exactly right. Yes, and then the risk is the exactly, yes, it's exactly that. But of course, you're replacing the conditioning upon A sub n for the probability with your preference. So you're doing your preference substitution at that point to get to the Jensen the expression on the next slide, the risk. Um, what I was could we just go to the final expression, because I did promise that I think there are ways of simplifying this which would keep Magnus happy. First of all, yeah. So if we allow ourselves to interpret the ambiguity here as the expected entropy of Y given its causes, as defined on the previous slide, and we um, simplify the JSD risk just to being the KL risk between Q and the preferred outcome. That would be the expected free energy. That is the expected free energy. And then you may say, well, what about my information gain, and what about my constraints? Well, the information gain is normally just a rearrangement of the ambiguity and the risk of a fairly simple sort. Yeah, I don't think you need to worry about information gain. In a sense, avoiding ambiguity in the context of maximizing the entropy of your predicted posterior Q is information gain. So you've already got information gain there just by writing down ambiguity and risk. I think more importantly, you've got your constraints that you want to you want. So this yes, that's right. So it's a number of times the the patient gets properly scanned, and and you want to minimize the that's the dose, isn't it? The D sub n is the number of dose.
Dosage.
Yeah, perfect. So what I would submit is that you can cover both of those things by including them in the preference distribution. So the way that the information gain is already covered is that you've already got maximum information or mutual information when you rearrange the ambiguity and the risk, so that you've already got the information gain simply by minimizing the ambiguity whilst minimizing the risk. Because if you take the first term from the risk term and put it against or inside the expectation for the ambiguity, that is the information gain. And so you'll get more information if the patients are scanned properly more frequently. So you've already got that as part of your objective function. And then the constraints on D, I think would, in my world, you would actually just have a state of the world xn+1 that said that they were able to have a proper scan or not. And then you prefer them always being in a state of more likely to have a proper scan. So now you can actually put into your preferences the possibility that you, oh, sorry, my apologies. We're talking about not the scanning, we're talking about the dose. So part of the external state space would actually be being recently dosed or having a dose. And you want to avoid being in that state. And so that you just now include in your prior preference the probability of receiving a dose is very small in relation to the probability of not receiving a dose. And then you can absorb your constraints into the risk. And then finally, so what I'm saying is these are ways of simplifying this for people.
No, I mean, everything was good. The last part, I need to think a little more. One of the things that I have is like, I mean, everything is what you're saying is you can choose preferred distribution in such a way that, you know, these other constraints are subsumed in the like absorbed by that preferred distribution.
I am to a certain, yeah, can I interrupt before, because but not the information gain, no, not the number of scans. The number of scans you should automatically maximize or optimize the number of scans through acting in a way that you can give them you can prescribe an imaging session for them. So the number of scans that the number of diagnostic tests that they receive is consequent upon the doctor's action. And certain actions will have greater epistemic value, and that will be automatically scored by the information gain that is already part of the that is already an aspect of the ambiguity and the risk. It's already there, provided you make the scanning of the patient dependent upon the action of the doctor. That in terms of in terms of the dose, a different mechanism. So what I'm saying, the information gain is already there. You don't need to write that out separately. That you should automatically optimize the number of scans. You might want to put a slight prior preference on not too many scans, because you don't want to give them too much radiation, for example. So there will be a trade-off between taking too scans are costly, so you may want to put the information gain in opposition to the cost of having a scan into your model. And the way that that's normally done is that the information gain is just measured in terms of natural units if you're using natural logarithms. But the cost of the scan now goes into the prior preferences, or sometimes called prior costs, or sometimes called prior constraints. So you'd say that, you'd say, I don't want my patient to be scanned too much. So the probability of having a scan on any one day is very, very small. But there will be there will be a pressure to have scans, to prescribe scans, because of the information gain. And the way that you moderate the two is by adjusting the precision of the probability of your prior preferences or your prior constraints. And that's the final point I wanted to make, that the problem formulation you can actually cast in terms of just the precisions of your prior preference. And if you can do that, then there's no formal difference between specifying and solving the problem in a conventional way and solving it using active inference, where the constraints on the POM-DP are not linear constraints that you get in linear programming, for example. They're actually constraints written into the probability distribution over various outcomes, in this instance being dosed and receiving scans. So they become soft constraints that are supplied probabilistically, and you can adjust the precision of those soft constraints, and those now become the C's, the small c's. So you don't actually have to introduce ad hoc coefficients that scale the information gain relative to, for example, the risk. That you can absorb those constants into a little bit like the alphas in the Rennie formulation. You can absorb them into exponents on some baseline prior preference. So, for example, if I was a very, very cautious doctor, I would prefer my patients to have as small a number of scans as possible. And if I was very worried about side effects of medication, I'd want them to have the smallest number of doses as possible. But if I was a less cautious doctor, I'm more interested in diagnostic veracity, then I would have a slightly less precise prior belief of a small probability of being scanned, but I might still have a high. So the doctor now becomes, if you like, characterized in terms of her prior preferences that now become the C1, C sub 1, and C sub 2 in the final in the final formulation. That's what I meant by you can slightly simplify the formalism by just absorbing everything into the prior constraints. I do repeat, though, this is a different way of doing it from linear programming and putting bounds on. This is not saying I can scan my patient 10 times in the next year, but no more. This is more like saying, I want to manage my patients, but such that the probability of them having one scan per 10th of a year becomes very small. And you can say what is very small. Well, that's just the precision of that particular constraint. You can say nearly impossible, sort of e to the power of -5. You can say, well, e to the power -3, sort of 0.05, 1 in 20. So you can quantify using the same semantics you have with Bayes factors or log units in GWAS study. Well, you can quantify log probabilities or log odds ratios, the degree to which you want this constraint to be enforced, which to my mind is a more natural way to prescribe constraints, because there may be situations where you really need that 11th scan. So having hard bounds is probably not the
I have that's why I have the expectations here in the constraints. So
I see. I see.
Maybe
right.
20, another maybe 1, but that's more amenable to the preferred distribution solution that you're basically.
Absolutely. Yeah, I see. So my apologies. I sort of seen the inequality side and assumed.
It's not arbitrary. The expectation makes sense because, like, you as a hospital have a budget, right? I mean, it's like if I can do a good averaging across 100 patients, which is this expectation, it makes sense. I mean, some patients may need 20, some patients may need 2, but that's kind of the motivation for this expectation. But yeah,
I see. Oh, well, that's nice. Well, yeah. So, one can think now, well, let's assume that patients have a sort of Poisson distribution over a number of scans they have during their treatment. And then if you have the expectation, then you know exactly what your prior preference distribution is over the discrete number of scans. And yeah, I see. Oh, well, that's already there then. Right. So in that case, then you can easily absorb that into your prior preference, and then you don't need to worry about about the sort of you've already put the constraints explicitly into the prior preference as a constraint, and that takes one of the constants out. And hopefully you'll be able to find a similar kind of constraints on the number of scans as opposed to the number of doses, which enables you now to symmetrically and gracefully absorb all the constraint into the prior preference, which is just your, if you like, your steady state distribution. This state patient is now managed in a routine way, and I'm going to have follow-up scans and the like with minimal maintenance doses.
I have a question, maybe an interesting direction that you think. So you're basically saying everything can be, or many of the things that I'm doing can be simplified if you summarize it into like the prior preferred distribution.
Yes.
So 2 questions. The first question is simple. When you say prior preferred distributions, the prior doesn't refer to time 0, right? The prior refers to being beforehand, I design my preferred distribution, which is kind of the ultimate point that I want the patient to converge to.
Absolutely. You've sort of described this as a sort of preference substitution. So you're substituting the prior that might have been in play for the generative model at the onset of an illness with some endpoint. Other people call it a target distribution. So if you describe it, when I say prior preference, I just mean that it's not a posterior. So it's a prior, and it's something I prefer. You could say it's a prior cost.
Before the whole thing, kind of a thing. It's not like a prior distribution. Okay. The second question is maybe that may be like an interesting. I don't know if anybody has looked into it, you looked into it, but so in many problems, so you have a starting point, which is a distribution, and there's like a preferred distribution, right? So what we are talking about here is finding a path in the probability simplex from this point to this point, right? So the question that I have is, in many interesting problems, including cancer, for example, there may be over the path. I don't just want to kind of go over this path with like the smallest number of steps or something, but maybe there are certain distributions that I want to go around, like avoid, you know, which would, for example, hey, it increases the probability of eventual success, but it also increases the probability of death, for example. So if I'm risk averse, I may, rather than take the straight path from the starting, which is like actual prior distribution, to the prior preferred distribution, maybe I want to kind of go around that a little bit to minimize some of the tail events. So my question is, are there any works that take into account those, like the tail distributions or the risk events being avoided along the path, rather than just find the path subject to constraints?
Right. You put those tail distributions into the constraints. So I think you could answer that, and indeed you should unpack that for the reader in terms of your information geometry. So what you're asking me, what is the best path from being over here to being at my target or my preferred distribution? Noting that in an information geometry, every point corresponds to a distribution. So exactly as you say, I would need to get from here to here. What's the best path? And then the answer, of course, from a physicist's point of view, would be the path of least action. What is the path of least action? It's the path integral that has the smallest, or it's the path that has the smallest integral of the expected free energy. What does the expected free energy depend on? It depends upon my prior preferences. So if I don't want to die, or I want to avoid tigers, that has to go into the into the energy landscape, as it were. So you're trying to find that geodesic, the path of least action, the most efficient path, and exactly the way that you were describing in moving from P to Q. You can also tell the reader that there's another interpretation of that path. Well, there is an interpretation of that path of least action. So you can imagine on your statistical manifold, for you it was a simplex because you were dealing with discrete states, a free energy functional. So there's a free energy landscape on that simplex. And the distance you move is basically the difference between the starting free energy and the end free energy, because the difference in the free energy is just the KR divergence between where you start and where you finish. So you've got to find a geodesic or a path of least action on a free energy landscape whose support is exactly your simplex, and that is the information geometry. And I really like that. I like the way that you introduce that. And sometimes what you can also say is, now, if you think about moving on these statistical manifolds that have this information geometry, then you now literally can ascribe movement on the manifold to changing your mind. That just is Bayesian belief updating. And in Bayesian belief updating, you're always minimizing your variational free energy. So you can now describe the flow from here to here as a gradient descent. Well, assuming that is the geodesic, a gradient descent on the variation free energy. So you get from your high point to your low point. And when you work out the maths of these flows, that's where you get the expected free energy, when some of these flows depend upon the action in the subspace of or the dimensions that correspond to action. So I would certainly use that metaphor of getting from somewhere high in the mountains down to the happy valley below. Moving in an information space in a way that avoids peaks of unexpected surprise, tigers, and death, um, um, by simply finding the paths of least action down that have the shortest information length.
Those risks are, in your model, which I love. Those are like in the geodesics, predefined geodesics of the landscape, right?
Yeah, they will be defined by regimes on that manifold that will be very, very surprising, have a very, very high free energy, like near-death experiences or encountering tigers. So your geodesics will avoid those highly unlikely, uh, unlikely in the sense that will be part of your preferred distribution, because the preferred distribution is really a description of how the system will behave once it has minimized its free energy. So you'll be very unlikely to confront tigers, or if you're being treated, unlikely to be close to mortality. So those would be parts of your preference constraints that would be very implausible, and therefore have a very high free energy and force you to move around the manifold in a way that avoids those. And that brings me to an interesting thing which you may or may not want to unpack. The way that you've told the story at the moment, you've used the word KL distance. Um, this may be a sort of a first language thing, but the KL is not a distance; it's a divergence.
No. It's not symmetric in the sense that A to B and B to A are exactly. But it's positive; it's non-negative. So
yes, that's certainly true. I'm just wondering whether it's worth unpacking for your audience how you'd get the actual distance from a KL measure, and it's actually a path integral of infinitesimally small KL divergences. So the information distance on your geodesic, on your shortest or path of least action, you can actually compute just by computing lots of little KL divergences, because it becomes symmetric if you move an infinitesimally small part. And so you just have to add them up. But I think there is I don't know if it's actually a formal bound. It's probably more of a heuristic. But Maxwell can point you towards it in the particular physics monograph. There is a close relationship between the information distance and the I can't remember what it's called now, but there's another measure which is upper bounded by the KL divergence. So what I'm saying is you can either say, as a footnote, note, of course, that the KL divergence is not a distance measure, but from the point of view of our current analysis and the intuition building, we will use it as roughly a measure of how much I've changed my mind or updated my Bayesian beliefs on the statistical manifold. Or you can get into the weeds and say, well, in fact, technically, the distance is actually a path integral of infinitesimal KL divergences. One reason you might want to get into the weeds there is that the metric that makes the information geometry is now also the curvature of the variation free energy, which is also now the Fisher information metric, which is also your the conditional uncertainty or precision. So you've got this really interesting notion now that the distance in moving from P to Q, from Q to P, for example, or from the beginning to the end, the actual distance that you move depends upon how precise your measurements are, and in particular on the posterior covariance as scored by the curvature or the Hessian, the second derivative of the free energy with respect to any direction of travel on the statistical manifold. So that means that there'd be some parts of this simplex that have, I'm not quite sure with the simplex, but certainly if you are working with continuous probability distributions, there'll be some parts where moving a little bit means you moved quite a long way because you actually had a very precise, your measurements were very precise and you went through lots of different belief configurations, even though you haven't moved very far on the simplex as graphically illustrated here. It's statistically speaking, you moved a long way because you've changed your mind a lot because your data are very, very precise. But if your data are very imprecise and the data moves you, it's not going to move you very far. And that's all measured by the curvature of the free energy on the manifold. So some really and if you really wanted to, you could then take that into gauge theory. So now a gauge theoretic treatment of this information theoretic treatment of belief updating in an information geometry usually, in my experience, reduces to an important consideration, which is the quality of your data and the quality of your beliefs in terms of their precision, which I repeat is just a reflection of the curvature of the free energy landscape at that point on your manifold. It may be something too far for a foundational paper, but it certainly is a really interesting thing to think about when you're talking about information geometries.
Got it. So I'll have the recording of this. So there's a lot of information here. I'm hoping to have a recording of this. I have a question, Carl. So I know our time's up, but it's not a technical question. If I go deep into this, would you be interested in, further conversation along those lines, especially in the discrete space?
Right. Yes. I would, and what I would offer and suggest is that you bring it back to these TMB meetings. These are to my mind, these are the best ways to have these conversations. Otherwise, I don't know what you know. You don't know what I'm trying to intimate. I think that having you present and then getting feedback and asking questions is the most efficient. So you should certainly feel free to come back when you think there's the next stage of the story is ready for discussion.
Yeah, maybe I can schedule the next one to put pressure on myself, but I feel too bold to do that. I was going to ask one more thing. Oh, one other thing is, so this is like a path, like all the nice stuff you said in the 5 minutes, path in probabilities, right? But then there's like for a given probability, there is also like the empirical, actual empirical distributions, which is itself different from your actual distribution and the empirical distribution. And I also have some insights on the difference between, or the distance between what you empirically observe and the actual distribution. What we have discussed was a path on the actual distribution or whatever, the variational distribution from one point to another. There's also another interesting question, in my opinion, which is maybe more relevant, what's the empirical distribution moving from one point to another, which is kind of maybe the way to come up with that geodesic, and then you minimize over the path integral and stuff like that. But anyway, these are all very useful, and I'll definitely sit down and think and digest further and get back to you about all of this.
Excellent. Before you go, and maybe you have to go to your next meeting, but for the recording, I'll just quickly go through the papers I thought that you would enjoy reading before you go, and then you've got a visual record of of the papers I had in mind. We've already discussed all the key points, but just to so I need to. You'll have to sacrifice the right. That's good. So now an application. I want to share the entire screen, so I'm going to share that. That's very good. And just so very briefly, given your interest in, I repeat, I think it's a really, really lovely demonstration of the utility of this way of thinking about sort of optimizing our diagnostic behavior. This paper was written recently by Thomas Parr, and it's specifically about if diagnostic interrogations are expensive, how could you use exactly the technology you've been talking about to pattern your costly investigations in the right kind of way. This was actually in the context of experimental design, but I think the same maths also applies to the context in which you were operating. So it was written for statisticians, but maybe an interesting, I repeat, point of construct validation that you might want to look at. That's Active Data Selection by Thomas Parr in, I have no idea. Oh, Algorithms. Right, yeah, I just put this up. Yes, there's one really interesting little point right at the beginning that you introduced, and it was the dependencies in the system theoretic way that you sort of wrote down the dependencies between active states and internal, external, and sensory states. And I was smiled when I noticed that the active states didn't have a reverse arrow, and that's really quite important in the sense that that allows you now to invoke planning as inference, because you can now have a posterior over your own actions. It's a bit of a philosophical thing, but it's quite important from the point of view of the free energy principle and the physics of things, which you have actually leveraged.
Just a quick note on that. This is exactly why I put the time index to there. Like, I mean, maybe you don't see it, for example, at the same time both ways, but from, n to n plus one, it's there. For some of n to n, for some of the n to n plus one. That's why I wanted to separate that time index.
Good. Yeah, and on this diagram, that would be that temporal aspect would be captured in these differential equations. So action can only get back into the game through the consequences. Yeah, absolutely. This is the paper that Magnus mentioned, cancer niches and their Kikuchi free energy, which leverages sort of Rene generalizations to Rene entropies and covers many of the issues that you were discussing. I have to say, my advice would be to not go down this particular avenue, simply because a lot of these arguments just go away when you're dealing with discrete probability distributions as opposed to probability densities. So you don't need to worry about heavy tail distributions or super Gaussian distributions when you're working with discrete Dirichlet or categorical distributions. So just practically, if you're working with POM-DPs, you don't really have to worry about this. If you are not working with POM-DPs and you're working with sort of continuous distributions, then it's a fascinating game. But usually at the end of the day, you come back to the KL and the conventional alpha equals 1 formalism. But it is a seductive game which you can certainly sort of explore should you want to. But I'm just saying that in my experience, you usually come back to the sort of simple Laplacian formulations that underwrite most of the physics that we do. That was, why did I put this in? Oh, yes, it was just it was this. I noticed you had mentioned fluctuation dissipation theorems, and you can actually derive the free energy principle and the expected free energy to a certain extent as a fluctuation theorem, should you want to. It just represents a sort of a slightly different direction of travel. Most people try to derive the expected free energy from the variational free energy. That's not really how the expected free energy gets derived. You actually start with the physics and just try to work out the probability distribution over a subset of states that happen to be the active states. And you can do that using an integral fluctuation theoretic approach, or you can use a path integral approach. This particular paper, though, takes this sort of shows a very simple kind of integral fluctuation theoretic derivations. Should you be and that's it. That's quite quick. Oh, good. Right. Then I can let you go to your next.
One quick question. The second one that you showed, the one with the state transition diagrams and the differential equations leading to that, was it a separate paper or was it part of the cancer niches by Noor?
No, it was that was, and my apologies if I didn't show the title. That has path integral formulation and strange things in the title, and that's a more recent one. It's the most it's the the physicist derivation of variational free energy and expected free energy based upon the pathological formulation. And I repeat, perhaps I'll just, for completeness, quickly show that again then for the recording. And I'm sorry if I didn't do that before. Oh, it's all gone away. Okay.
That's okay. I'll figure it out.
It's all right. I found it. Don't worry. There we go. Oh, no, that's the wrong one. We want path integrals.
Yeah. It's in the chat. If you want.
Well done. Thank you. Thank you for rescuing me. Right, good.
Thanks.
All right. So if Carl is done, I think it's time for another round of applause for our wonderful speaker.
I appreciate it. It's great. The feedback was awesome. Thank you. Thanks for all the detailed feedback.
Thank you.
Well, we thank you for taking the time to present to our TMB meeting, and please feel free to schedule another meeting to challenge yourself to produce even more. Yeah, I will send you the link of the recording once I upload it on our YouTube. All right.
Thank you. I appreciate it. Thank you very much.
Thank you, Emre. Thank you, everyone, and see you at the next TMB meeting. Bye bye.
Bye bye.